Hi and welcome to this first tutorial about Manis, a collaborative design tool for integrally attached timber-clay structures. The purpose of this Grasshopper plugin is to help engineers, architects, designers with the design of structures made out of timber panels and connected by wood-wood connections. The goal of this video is for you to get a basic understanding of how Manis is working and that you understand the logic behind and the workflow and procedures associated with it. So let's start directly with the first example. I drew here in Rhino two plates, as you can see. The yellow one has a hole in the middle, and then we have a green one attached to it. So I reference both plates here as an input for the plate model builder. So what the plate model builder does is that it will just take a collection of breps and convert it to a plate model with associated attributes, properties, and functions that you can use to generate the joint geometry, the assembly, and so on. So it's also important to specify a correct assembly sequence. So by default, we will take the order in which the plates are referenced inside the input. So here I reference the plates in that order, but you could also specify a specific assembly sequence in the sequence input here, and this we will do it later. So what it means here is that the plate 0 will be the first one to be assembled, and then the plate 1 will be inserted or assembled on top or next to the plate 0. So let's have a look at the different properties that you can access from the model. So you see that here we have, for example, access to the plate faces. So you see that we only extracted here the top and bottom faces of those two plates. We can also extract from another component the plate contours. So you see here we have the top, mid, and bottom contour of the plates. Can be very useful to get a polyline representation of the model instead of a brep representation of the model. We can also isolate the holes. So here you see we have the top and bottom polyline of the hole in plate 1. We can also have access to the planes here. So we have also a plane associated with the top, mid, and bottom surface of the two breps. That's also why it's important that all preps are planar for the model to perform, because otherwise we wouldn't be able to generate a plane on top of it. And we can also get the plate thickness. You see that here they have the same value. So let's move to a second example with a bit more plates. So I have here in Rhino 6 different plates that are connected in different manners. You see that plates 1 and 2 are connected by the faces, while plate 1 and 0 are connected by the sides here of the plates. And you see also plate 5 is intersecting plate 4 and plate 3. So Manis is not only useful to generate geometrical information about the plate themselves, but also to generate information about how the plates are connected together. So the first component here that I have is called contact zone, and it's simply to highlight the places where the plates are connected. So you see here we have this red area, which is the intersection of the two zones of the first plate and the second plate. And the same comes here between plate 0, 1, 4, 0, 3, 0. And here for the intersection between plate 4 and 5 and 3 and 5, it should be a volume, but since later we will only want to work with surfaces, we used only the mid-plane here of the volume to describe a little square inside the intersection volume. So all contact zones are by definition surfaces. You can also get access here to the ID of the neighbors. So typically if you look at plate 0, you see indeed that it is connected to plate 1, 3, and 4. If we take plate 1, you see in the Grasshopper Canva that it's here connected to plate 0 and 2, and indeed it is connected to plate 0 and 2. So all this adjacency information is generated by the plate builder by doing several Boolean intersections between the different breps to get that data. So that's also why it takes a bit of time sometimes to generate the plate model. And finally, here we have the topologic connection. It's especially useful for modeling timber joints because the type of joint that we can model between two plates will vary in function of the way the plates are connected together. So here, for side-to-side connection, we use the abbreviation SS. You have also more textual information. You have the full string here. So indeed, the side of plate 0 is connected to the side of plate 1. And for others, you see that we have, for example, the volume of plate 4 that is intersecting the volume of plate 5. So we try to make it a bit more explicit, uh, especially for people who don't know what is behind Manis. So let's now move to my favorite part. Once a model is generated, we can finally create a timber joint. For each contact type, we can currently generate one different type of joint. Maybe in the future we'll add more timber joints, but in the latest release, we have 5 types of joints that the user can create. So you see that we have again here as input 2 breps. So let's take the first set. And you see that here they're connected face to face. So for face-to-face contact, what we can create is a dowel joint. A dowel joint is a pretty basic joint. It's nothing really fancy in terms of geometry, but nevertheless, it's a quite common joint in timber construction, so that's why we decided to implement it in Manis. You see we have quite a large amount of parameters for this joint. We can notably change here the amount of dowels we have in the connection. We can also modify the radius. See that here they become larger. We can also add some tolerance, that is mostly when we want to fabricate the plates, if we want to have a larger hole than the size of the dowel. So here you will not really see a big difference, but if we go on top view, you see that we have now 2 cylinders. One is for the hole and one is for the dowel. So here, of course, it's an exaggerated tolerance for the assembly. It will become too loose and the dowel will slip off. But you got the principle. So let's go back here to Grasshopper. We can also add some retreat parameter here. You see that here we have decreased the amount of dowel present in the bottom plate. We can do the same, of course, in the other plates with dowel retreat 2. Well, of course, in that case, we will hide the dowel and it will be a bit difficult to insert it. So maybe it's better to keep at least one side where it will be visible so we can access it. So let's put back both dowels parameters to 0. Then we have also a parameter for the circle radius. This is here the span between the different dowels. So if we add more, we will better visualize the circle. We have also a parameter for the circle rotation. So if you want to modify the distribution of the dowel on the plate. We can also change the tilt of the angle. This is the dowel angle 2. See, and we can also make them non-parallel here to have a different inclination for each dowel. We could also use a tile. So here, if I want to specify a specific geometry for my dowel, here I decided to use a square. So I will just set this as input in the tile parameter, because by default it's always circle, so it's always a cylinder. And you see that here I modified my dowel to be a square. So here again we can modify the inclination of the tenon. It can be non-parallel, and we can also use dowel angle 1 to make another kind of rotation. So that's it for the dowel joint. So let's move now to the second type of joint that we have. It's also a very common one, is the through tenon, or tenon and mortise joint. So you see that we have a bit less parameters here, so we can modify the number of tenon in the connection. If we exceed, you see that automatically the component returns an error, and it will tell you also by how much you should decrease your joint in order to have a valid connection. So it's a bit too large for the side that is touching the contact zone. So we can also modify the length of the tenons. So here you see that with a smaller length, we can hide the tenons in the plate thickness, while we can also do the opposite by having a larger length. It will exceed the plate thickness and it will be visible on the other side. We have also other parameters. So if I decrease maybe first the number of tenons, I can increase the spacing between those two. With a spacing of 0, they are attached. And here we can also modify the shift parameter so that it will move here on the contact zone. It can be done for several reasons. So let's now move to the finger joint. So this one looks a bit like the tenon joint, with the exception that this one is only for side-to-side contacts. So you see that plate 1 and 0 are not touching by the faces, but by the sides. And the parameters here for the finger joint they differ from one side to the other. So I can specify the number of tenon on one side differently and separately from the other side. So you see here I have one tenon on one side and two fingers on the other side. I can also modify the length here of the tenon. Again, by default, it's corresponding to the thickness of the plates. So if I put 0 as a value, I have my default value coming back. Here I have also the finger width. So you see I can decrease the width of one side while having here another width for the other fingers. I can also increase here, modify a bit the number of tenons for both sides. I can also choose the spacing between them. Maybe I don't want any spacing, so it's more like an alternative pattern, or I want a spacing like that. I can also modify the shift as for the other joint that I showed earlier. And I can also use mirror. Mirror is when we have an even amount of tenons. So if I have this and I do mirror, you will see that it will flip here the fingers from one side to the other. So again, that's pretty straightforward, I believe. And you see that the user has only a few parameters to specify to get the geometry as he wants. So let's now move to the fourth type of joint, which is the half-lap joint. So this one is for intersecting geometries. It's also a very common joint in timber construction. We can here change the proportion of the cut. So you see that my midplane is changing here from one plate to the other. So this will decrease the ratio of material that is kept in one plate and increase the ratio on the other plate. I can also add a tolerance parameter, and you'll see that this creates automatically a big joint in it, because we want to be sure that we will cut the plate until the edge. So by purpose, we extended the joint to be sure that it will go until the edge of the plate. And as soon as we add some tolerance here for the joint, you see that it will also create some kind of curvature here. So we can choose here what is the size of the straight edge, so this part of the joint, what will be the size of the fillet height, so the curved part. We can also modify the amount of segments in that fillet height. So if we put here 1, you see that we have a slope made of just 2 sides. So we have a kind of simplified version of the joint, but we can also have a smoother gradient that will help for the insertion of the joint between the two plates. So this is the half-lap joint. So let's turn off the tolerance, for example. And let's move to the last joint, which is my favorite from the 5. This one is called the Nejiri Arigata in Japanese. It's a sunrise dovetail joint. It's a very interesting joint because it has only one possible vector of insertion, and it's only possible for edgewise connections. So an edgewise connection is when the plate here is really at the edge of the face of the first plate. So again, let's have a look at the different parameters that we have here in Manis. So for the sunrise dovetail, we can also modify the number here of tenons that we have. Here it's a sunrise with just 2 tenons. Looks pretty awkward actually. So let's have a bit more. We can also increase the tenon width or decrease it. We can increase the tenon spacing. We can also shift a bit the joint as for the others. And we can also here have a spread angle parameter. So you directly see in Rhino what it does when I modify this parameter. It's the angle here of the tenons is wider or thinner depending of the number I put here. I can also ask the solver to make only parallel faces for the joints. So you see that in that case, the angle is distributed among all faces, while if I turn these parallel parameters on, I have here all faces parallel for all fingers of this joint. This one is quite famous in carpentry also. You can have a look at a few videos on YouTube or Vimeo. In the meantime, don't hesitate to contact us if you have any ideas or requests about the addition of a new joint inside Manis. So just to add another layer of information here, each joint is not yet merged with the plate at that stage. So you see at the end of each joint component, we have actually 3 lists of solids. One is for the joint positives, one for the joint negatives, and one for the joint keys. So typically, if we want to display here the dowels, there are joint keys, there are additional pieces that need to be added to the model. But we also have a joint negative, which is the hole in which we need to insert those dowels. For the tenon joints, we don't have any additional separated pieces. It's an integral mechanical attachment. So we have here a solid that is attached to plate 1. It's a joint positive. But we have also a hole for the mortise, which is here represented in the joint negative list. So those lists, they are going to be useful when we will merge the joints with the plates. And so this will be achieved with the help of the merge joint with plates component. And so if I attach this at the end here of my add tenon joint component, what it is doing is that it's merging the joints positive and the joints negatives list with the geometry of the plates. And so when I bake it here in Rhino, you will see that now I have indeed my joints that are merged, and we indeed needed one list of solids to do this mortise and one other list of solids to do this tenon. So that's it with the joinery. Now we will have a closer look at the assembly sequence itself and how we deal with insertion constraints, because each joint, as you see, the geometry is a bit different, but it also means that the assembly will be a bit different from case to case. When we designed Manis, we really wanted to have a solver that will not only generate joints geometry, but that will also take into account the way the pieces will be assembled, so the order of assembly, the assembly sequence of the pieces. So in Manis, one of the inputs that you can give to the plate model builder is the sequence. So you can change the order of the plates, and this matters for the joints geometry. So I can display the sequence here with the display sequence component. And you will see that if I don't specify anything here as a sequence, I have the regular order in which the B reps have been referenced. So I have here the first, second, and third reps, And that's how they appear in Rhino also with the display sequence activated. But I can also modify the order of the sequence using a simple string of the IDs of the plates that are here between two hooks. So here you see that I specify 2, 1, and 0 as an order for the sequence. So the plate 0, 1, 2 becomes 2, 1, 0. I reverse the order. And I have an output here that confirms that the sequence has been rearranged. So you can also display here the change using display sequence after the plate model builder and before. This is especially useful when you want to work with modules, but this we will come to it in the next example. We can also check the assembly sequence using animate sequence. This one is really nice because you directly see the order of the plates and it's already showing you in what direction they will be assembled. And this we will also come to it in the next examples. So here you see if we have first plate 0, 1, and 2, we'll have this kind of assembly. While with the default values, the assembly sequence will be a bit different. We will have first plate 0, then plate 1, and plate 2 here you see that the assembly is a bit weird because actually the two plates we have here, plate 0 and 1, they are not parallel. So it means that we cannot insert a plate from above. And here, as the solver had no choice, it just provided the only possible answer, which was a lateral insertion, which feels a bit weird anyway. No real joints can be really modeled here in the end. So that's why the assembly sequence matters so much. So if we move now to the next example, we will go a bit more in detail about the assembly constraints. So we will take another structure. So let's hide this one and display this one. So here you see we have 3 plates and they are all touching each other. And so that's exactly for this kind of topological arrangement that Manis was developed. You see that in order to insert plate 2 inside plate 1 and 0, we will have to make a kind of compromise. We cannot just have a tenon here and a tenon there. We need to have a common vector of insertion between both plates, and we need the geometry of the joints between those pair of plates to be like coordinated in order to keep a compatible assembly of the 3 plates. So what the solver is doing is that it will try to find a compatible vector of insertion by looking at each contact zone and its insertion constraints. So we can display them in Manis. So that's what we provided here with the insertion space component. It has 2 outputs. One is called spheres. It will just display the insertion constraint as a sphere or circle on the contact plane, on the contact zone, while the grouped output will be used to group all constraints at the 0, 0, 0 origin, and it's more useful to see how they will intersect. So let's first check here the spheres output. So here, since we have side to face connection, it's only a part of circle. So each topological case has a specific insertion domain associated, but we can also specify here our own constraints for the solver. So you will see that if I reduce here the constraint for the angle alpha, we decrease the amplitude of the circle. It's now a bit reduced. So it also means that we reduced the area and the size of the domain of insertion to find a compatible vector of insertion. So we can have a look also at the grouped output. So those two here. So here we see also the 2 circles. So we have the first one here and the other one there. And you directly see that there is a possible insertion in that area. And so what Manis will do, it will compute here an insertion vector that will be the average of those 2 potential insertion domain. So this insertion vector is the one that will be displayed here in the assembly sequence when you animate the sequence with the animate sequence component. So if we here set the animate sequence to the third plate, you will see that this plate is indeed moving according to a vector of insertion that is kind of the average of the two insertion domains that are currently displayed. And so this will ensure that when we will model the joints according to those insertion vectors, those joints are going to remain compatible with the assembly sequence and with the arrangement of plates. Let's also have a look at the insertion domain for plate 1. If I modify the ID here of the path for the data tree structure, we can see that the insertion domain for plate 1 is being previewed, being shown. So you see that we have again this constrained custom domain that we specified with the input here in the Grasshopper canvas. We could, by the way, also increase angle beta, and we will then transform our circle to a piece of sphere. You see that we have now a surface here. And you see that for edgewise connections, here we left it as default. And by default, we have a quarter of a sphere that you don't see really well with that display. So let's zoom maybe on the grouped output. And so here we have the two pieces of sphere that represent the custom insertion domain for the true tenon joint and the default insertion domain for an edgewise connection like the Negiri Arigata joint. In that case, those two domains, they are not going to be intersected to compute single insertion vectors, because those joints, they intervene at a different step of the assembly sequence. So we will compute one average assembly sequence for the green area here, and one other for the other piece of sphere that is currently displayed in red. So you can also see it in the animation of the assembly sequence, that when I will display this, I'm just hiding a few other components before, when I will display the assembly sequence, you will see that for this plate, we are indeed coming with a 45 degrees angle, which is actually the average vector of this piece of sphere, while this other piece of sphere is only used at the next step of the assembly sequence when the other plate comes into the game. So the assembly sequence and the insertion vectors are closely related to the geometry of the joints, and we need to take that into account in order to model a joint that is compatible with the assembly. In the third example, we will apply what we have learned so far. I have here a little pyramid made out of 4 triangles, 4 plates that need to be assembled exactly in that order, 1, 0, 2, and 3. So you see already that plate 1 will have 1 neighbor at the time of assembly, same for plate 2, but when plate 3 will be inserted, plate 1 and 2 will already be there. So let's see what Manis gave as a result. So I will skip here the creation of the joint, and let's see directly the result from the animate sequence component. So the first plate, always there was the ground, then the second plate that will come here laterally, and you see that the vector is compatible with the geometry of the joint. For the other plate is the same, it's just the symmetry. And then for the third plate, you see that we computed here a compatible vector of assembly that is not the same as the two previous ones. It's the average of the assembly spaces of the contact zone between plate 1 and 3 and plate 2 and 3. And you see that it corresponds, if we have a look from this orientation, you see that the joint will be inserted without any geometrical conflict, and we can proceed to the assembly of the pieces until the end. So now that we have discussed the assembly of a few plates together, let's move to the next level and consider a group of plates that needs to be assembled in one shot. So I have here a small tower made out of 6 plates. And in fact, it's not really 6 separated plates. What we have here is 2 groups of 3 plates. And this is reflected in the assembly sequence that I set here as an input. You see that we have 0, 1, and 2 that are between 2 hooks, and 3, 4, and 5 that are between another pair of hooks. And when writing this as the string input for the sequence input of the plate model builder, I am specifying that I want Manis to understand that this group of 3 plates will be assembled in one step on the other group of 3 plates consisting of plate 0, 1, and 2. And again, we will need to compute compatible insertion vectors, but with much more constraints than before, of course. So for this example, since we have face-to-side contacts, I decided to generate tenon joints, so we can display them here. But more important than the joints, here is the assembly sequence. So we have several modules, so we can specify a module ID. Here you see it's 0. And the first module here is the module consisting of the plates 1, 0, and 2. And so if here I move from 0 to 1, I will display the assembly sequence for the module 1, 0, and 2. Then when I will start moving from 1 to 2, here this component, it's just splitting the integer and the decimal part of my slider. Now I have module 1 consisting of plate 3, 4, and 5. And when I will be moving, I will have the assembly of plates 3, 4, and 5. And you got it, the last module is the assembly of the 2 modules together. So when I will move from 2 to 3, the sequence that I'm doing is 0, 1, 2 plus 3, 4, 5. And so I will display this as such. And you see that the insertion vectors here are all compatible, even if they are not very difficult because they are all orthogonal in that case. So this was a first example about modular assemblies. Now let's have a look at the second example. In this one, we also have 2 modules of 3 plates, but with different types of contact zones. So you see here we have a side-to-face connection, while here we have an edgewise connection, here on the edge of plate 2 and on the edge of plate 5. And we have also a side-to-side connection between plate 4 and plate 1. So if you have a look here on the assembly sequence, you see that we have 0, 1, 2, and 3, 4, 5 that are grouped into 2 different modules with the hooks. Here you can see that we will add a tenon joint for the side-to-face contacts. And you already see in the model that some are inclined and some are not, because they have different insertion vectors, and they are all computed with this single component. Then we have also a sunrise dovetail joint, this here, on the edge of plate 5 and plate 2. Then we have the Boolean operation, merging the joints with the plates. And here we get the access to the modules. So here we will have a look at module 0. So if you look here, what is the value? We have 0. And module 0 consists of plates 0, 1, and 2, as defined in the assembly sequence. And so if we have a look here at the relatives, so the relatives are the plates that are used to compute the insertion vector for each group of plates or each plate. So here, for the first plate, plate 0, we don't have any neighbor at the time of insertion because it's the first plate. So per default, we get a gravity vector towards the bottom. Then for plate 1, you see that the neighbor that is used to compute the insertion vector is the plate 0, because it's the only one already present, and it has indeed a contact zone with plate 1. And for plate 2, when we need to insert plate 2, plate 0 and plate 1 are already there. So we need to take an average vector for plate 2 between plate 0 and plate 1 according to the insertion domain as illustrated in the previous example. So that's why plate 2 has a tilted insertion vector with an angle of more or less 45 degrees. And the same goes here for plate 5, where it needs to be inserted in plate 3 and 4. So this explains why you have tilted tenon for plate 5 with plate 3 and 4, while you will have orthogonal tenons when we will insert the module 3, 4, 5 into 0, 1, 2. Because if we have a look at the relative for module 3, 4, 5, so we need to go here, for example. Module ID is here 2. So module 2 is indeed the assembly of 0, 1, 2 with 3, 4, 5. And here you see that for the module 3, 4, 5, we indeed have two contacts, one with plate 1 and one with plate 0. And here, the average insertion vector is perpendicular. So the second pair of tenons here is going to be orthogonal because we don't use the same plates for the computation of the insertion vector. So now we can check the assembly sequence with the animate sequence component. So we have the first plate here, plate 0, which is assembled with a gravity vector towards the ground. Then we have plate 1 that comes laterally because the only constraint is with plate 0. Then we have the second plate that comes with a 45 degrees angle. And you see that both the Negiri Arigata on the edgewise connection here and the true tenon on the side-to-face connection have been influenced by this 45 degrees insertion vector. And you will see that the assembly remains compatible for both. Here you see the tenon being inserted, and also the Negiri Arigata that fits perfectly. The same will happen, of course, for the next module. So we have first plate 3, then plate 4, and then plate 5 with also a 45 degrees angle. And then we have the last sequence, which is the assembly of the full model. So first the module 0, 1, 2, and then the module 3, 4, 5 with this orthogonal true tenon that will allow both of them to fit together. And so here we are able to conclude the assembly of the structure. So with those different examples, we covered already the basis of Manis. You saw how to generate a timber plate model. You saw how to create different types of timber joints. You saw how to modify the assembly sequence and to play with modular assemblies. So in the next video, we'll also see how to extract fabrication toolpaths and robot trajectories. But this one is already long enough, so let's make a break and let's see each other in the next video. Bye bye!